So we just talked about how solutions form with covalent solutes. Now we're going to focus on ionic solutes. When you have an ionic solute, you have these solids that are originally composed of those cations and anions packed tightly together because they have those strong electrostatic interactions, which we call the ionic bond. And then water comes along and starts pulling on each of these ions, and eventually you form these structures like these where each of the ion is surrounded by a bunch of water. These are actually called solvation shell because there's multiple layers of this that will form. And so that's how an ionic compound dissolves. Now, the process of dissolution requires those three steps that we talked about in the previous section, which is your delta H of solute, delta H of solvent, and delta H of mix. So same exact three steps, okay? Nothing's changed there. However, because we're talking about ionic solutes dissolving in water, a lot of times what people do is they combine two of those terms that I just listed. So delta H of solution is delta H of solute, solvent, and mix. And so these two a lot of times is combined together, and instead it's being called delta H of hydration. It's referring to the fact that how well can that specific solvent, which usually is water, interact with the ions at the cost of breaking apart the hydrogen bond that exists in water. Okay, so delta H of hydration is just the delta H of solvent plus delta H of mix. When you calculate delta H of hydration, there's the two different components in it, right? So the delta H of solvent, as I said, is the energy needed to break the hydrogen bond that exists in water, okay, because we're talking about water as a solvent. The delta H of mix is the energy you gain from water interacting with the ions. So remember from Gen Chem 1, this is what we refer to as an ion-dipole interaction, which is a stronger interaction than the hydrogen bond interaction. Because ion-dipole is stronger than hydrogen bond, that means when you add these two numbers together, this delta H of solvent is positive, delta H of mix is negative, but the negative is bigger than the positive, so the overall delta H of hydration also becomes a negative number, okay? Again, the interaction you gain ends up overcoming the interaction that you have to break. Okay. Now, if you have multiple ions, then the delta H of hydration for the entire solute would just be the sum of the delta H of hydration of the separate ions that you have. Now, let's take a look at the solute component of it, right? Remember that we have this third delta H, which is the delta H of solute. Now here, what we're looking at when we're talking about delta H of solute is how much energy does it take to break the interaction that we have in the solid ionic compound. Okay, we're trying to break that apart. These are really strong interactions, right? Because they're positive, negative of full ions. You may remember this from Gen Chem 1, but we call that interaction ionic bond, but we have an energy term that we use to measure that, which we call delta H lattice, standing for the lattice energy, okay? So the lattice energy, because this whole thing is what we call a lattice, and so the lattice energy is a measure of how strong an ionic bond is, and you want to remember that a lattice energy is measured using this reaction right here, and lattice energy is always very exothermic, right? Because the formation of that lattice, that positive negative ionic interaction, is really favorable, okay? And so the delta H of lattice is always very exothermic. And so if we want to combine all of these into our delta H of solution, so remember our delta H of solution earlier is just the delta H of solute plus the delta H of hydration. We already look at the delta H of hydration as being negative. The delta H of solute is the energy it takes to break the lattice, so it's the negative of delta H of lattice, okay? And so your delta H of solution then is just going to be your delta H of hydration minus your delta H of lattice. The delta H of hydration is negative. The delta H of lattice is also a negative number, but when you subtract one from the other one, you might get a positive, a negative, or a zero, depending on the type of solute we're talking about, the type of ionic compound we're talking about. So the process of dissolving an ionic solute looks like the one shown in this picture. You have your ionic lattice, which you need to break apart into the separated ions, and then you need to take those separated ions and hydrate them. So basically you need to take the water, separate the water apart, and then have the water surrounds each of the ion, which is shown in this picture right here. And then the sum of these two processes, which is this part and this part, is what gives you the enthalpy of the solution, okay? Now you can get different numbers of delta H of solution depending on how strong the interactions you have in your ionic solutes, right? So I'm going to give you three examples because there's 3 different possible values. NaCl, which is sodium chloride, ends up having a pretty small delta H of solution. Okay, it's positive, but it's fairly small. Even though with a positive delta H of solution, when we take NaCl and mix it in water, it still dissolves pretty easily. And that's really because of the entropy factor, right? The entropy is really favorable. You can actually calculate it if you have a thermodynamic value table, like the one that we've been using. And I found that that number is positive 43.4 joules per Kelvin. So because the entropy is positive, that's what's making it favorable. But because the delta H of solution is fairly small, this is what we would consider to be fairly close to zero. So when you mix NaCl with water, as you know from experience, the solution doesn't really have much change in temperature. If you mix it, you get a little cooling maybe, if you can feel it, but most of the time the feeling of that solution when you mix it versus before you mix it is just the same. The temperature doesn't really change by much. Okay, so this is the type of solution where the delta H of solution is fairly close to zero. NaOH is something completely different than NaCl. In this case, if you mix it, it actually has a pretty large delta H of solution in a negative sense. So it's an exothermic solution. Okay, so you can see that it's negative 44.5. And again, this is something you can calculate by looking up the thermodynamic values for NaOH and the Na plus and OH minus ions. You can see that because of the negative 44.5, when you mix the solution together, it actually feels hot here. We typically do an experiment where we measure how much the temperature has increased because of just mixing NaOH solid with water and dissolving. Ammonium nitrate is the opposite. Here you have a large positive delta H of solution, 25.7 kilojoules per mole. So in this case, when you mix it, the solution actually feels cold. And then you might ask yourself a question here, why does this solution still form even though it has a pretty endothermic delta H of solution? And of course, the answer is because the entropy is helping us make the solution mix with water, make the solute mix with water. The delta S of solution, if you calculate it, is actually about 108 joules per Kelvin. So this is one solution where the entropy is able to overcome that unfavorable enthalpy and make the solution still form. So these three here are energy diagrams that shows how each one of these things form. Again, that little arrow there shows the actual difference in the delta H of solution. This is your exothermic solution, this is your endothermic solution, and this is the one that's fairly close to zero. That's the NaCl. Right. The reason we care about these exothermic and endothermic solutions because they actually have some applications, right? So the most common one is in this cold pack, hot pack application. A cold pack is actually just that same salt that I just showed you, ammonium nitrate, being mixed with water. So you know that a lot of times the way we use these things is we press on the pack to make two things mix inside. What is being mixed is really just water and some kind of a solute. So the solute that you have in there depends on whether you want a hot pack or a cold pack. So for a cold pack, the solute will be ammonium nitrate. For a hot pack, it will be calcium chloride, which is an exothermic solution. As you can see here, has a negative 82.8 delta H of solution. Now that we understand how to analyze delta H of solution for both covalent and ionic compounds, we're going to take a look a little bit on an example here on how to use some of that information to understand a little bit the behavior of ions and interaction of ions with water. So this example here shows you the delta H of solution of two ionic compounds, right? KNO3 and NaCN, and also gives you the lattice energy, which again is something you can find usually from reference table, or you can calculate. You learn how to find these numbers, by the way, in Gen Chem 1 when we talk about the Born-Haber cycle. And so the question here is, which compound has a higher delta H of hydration? I've done this work on the right side, and we start by keeping in mind that the delta H of solution is equal to delta H of hydration minus the delta H of lattice. So if I want to solve for delta H of hydration, then it should just be equal to delta H of solution plus the delta H of lattice. I'm given both of those numbers there for both of these salts. Here's the delta H of solution on the left. Here's the delta H of lattice. And so all I need to do is just add those two numbers together. And this is what I got here on the right. Delta H of hydration for KNO3 is negative 650. That shouldn't surprise you because, as we said earlier, this hydration enthalpy is a negative number. And the reason is because that ion dipole interaction that you make when you mix water with some ion is stronger than the hydrogen bond interaction that you lose when you have to break that water liquid apart, right? For NaCN, the delta H of hydration is even more exothermic, it's negative 764.79 kilojoules. So that's how you actually calculate the number. Now let's take a look at question B. It says here, if delta H of hydration for the anions are relatively similar, which ions, K plus or Na plus, has a more exothermic delta H of hydration? Okay, so let's go back to the right side to take a look at this. We see that delta H of hydration is the sum of the delta H of hydration of the ions, right? So for the salt, it's just the sum of the two. And so for NaCN, it's the sum of the cation and the anion here. We just calculated these numbers on the top. It tells us that the delta H of hydration of NaCN is bigger on an absolute scale than the delta H of hydration of KNO3. Since the anion part is relatively similar according to the question, that must have meant that the delta H of hydration for the sodium ion is bigger than the delta H of hydration of K plus. And so the question is, why is that? Now, what you have to remember is delta H of hydration is a measure of the strength of interaction between water and the ion. So why is water interacting more strongly with sodium ion compared to potassium ion? Well, we can explain this by looking at the sizes of these ions. So sodium, if you remember the periodic table, is located above potassium. So here's sodium, here's potassium. So potassium is a bigger ion than sodium. And the interaction that we're looking at here is an electrostatic interaction, right? It's an interaction between a polar molecule, which is water, and the ion. So it's an electrostatic interaction. And that electrostatic interaction, which is also called Coulombic interaction, is inversely proportional to distance of the two charged particles. In this case, we're talking about water. So water right here, and the cation. Okay, so it's this interaction that we're measuring. So here's my water, here's the interaction I'm measuring. As you can see, if the ion is smaller, that interaction is stronger because the two charged particles are closer together. The water and the ions are closer together versus when you're dealing with something larger. That's the reason why the delta H of hydration for sodium is more exothermic than delta H of hydration for potassium. Let's take a look at another example of thinking about hydration and exothermic endothermic solution. Here it says water is added to a flask containing solid NH4Cl, ammonium chloride. The salt dissolves, the solution becomes colder. First question is it dissolving, exothermic, or endothermic? Well, because the solution becomes colder, it must be an endothermic solution. And then the second question is the magnitude of delta H of lattice of ammonium chloride larger or smaller than the combined delta H of hydration of the ion? Okay, well, first off, we know that the dissolving is endothermic. That tells you that the delta H of solution is positive. The delta H of solution is made up by the delta H of hydration and the delta H of lattice. Okay, and so those numbers are positive. Now keep in mind that this is negative, this is also negative, but in order for me to make the entire number positive, this number, this negative number, must be bigger than the delta H of hydration. The lattice number has to be bigger than the hydration. So in other words, I can conclude here that the absolute value of the delta H of lattice must be bigger than the absolute value of the delta H of hydration. That's the only way I can get a positive delta H solution, which is an endothermic solution. Okay, so the last question is, well, if the delta H of solution is positive, why does ammonium chloride still dissolve in water? This is a question that we've answered a couple of times before. The reason is because delta H is not the only factor that we consider when we're thinking about solution formation. It's delta G, and delta G has two different things in it. It has delta H and also has delta S. So if we've seen a few times now, the delta S of the solution is driving solution formation here.